Hello, everybody. It's my pleasure to start this webinar today, our third day of webinar, and we will have today, and remember, next Wednesday, one more day of webinar. And I need to say that I'm very happy and glad today because I have Professor Daniel Snow with us from UNL. And I remember that he is the first person to give me an opportunity to give classes in UNL. And so I need to recognize this. Professor Daniel, thank you very much. And thank you, Dr. Palhare from Embrapa to stay with us today and to participate in this webinar. And we hope that we have a good time to discuss a lot about the water quality and the water productivity, considering the agriculture and other important activities in Brazil and United States. Okay, and so we are very glad to have this time together. And now, Luciana, you have the microphone. Thank you very much. And I hope for everybody a very good time together today. Luciana.
Thank you, Professor. So we want to thank Water for Food and Universidade Federal do Paraná for this opportunity to bring One Health in this discussion between United States and Brazil. And I just want to make a quick reminder that if you have any questions for our panelists, so you can use the Q&A box during the presentation, and after that, we will have Professor Marcelo Molento conducting the discussion session. So it's my pleasure to introduce our first panelist today, Professor Daniel Snow. Professor Daniel Snow is a research professor in the School of Natural Resources and director of the Water Science Laboratory, a part of the Nebraska Water Center and Daugherty Water for Food Institute at the University of Nebraska. He holds advanced degrees in geology and geochemistry. Over the past 30 years, his research has focused on water quality and environmental fate of emerging contaminants and agrochemicals in ground and surface water. He directs staff and students in development of methods using advanced mass spectrometry to better understand and conserve the freshwater resources upon which he will all depend. So welcome, Dr. Snow.
Thank you. And thank you, Paulo, for inviting me to present today. So today, I'd like to talk about water quality in agriculture. My background is in farming. I grew up on a farm in Southwest Iowa. I went off to study geology and chemistry and have made a living doing research in water resources here in the Midwest since the late 1980s. I'm going to talk about population growth, water quality, and agricultural intensification, the relationship between water pollution and One Health. And then the remainder of my talk is going to be about emerging contaminants and agroecosystems, a little bit about sampling methods and the ways we measure these contaminants and why we study them in the first place. Well, I'm sure many of you are aware of a growing population in the world. We're on our way to supporting almost 9 billion people on this planet. And the amount of fresh water that we have is pretty much fixed. So you can see from this simple graph that we're already at the point where we have less than 1 cubic kilometer per person of fresh water. The more people we have, the more processes that are contributing to water pollution. This is a diagram that shows the relationship between water pollution and One Health. We have contributions to water pollution from human waste and from agricultural waste, both from wildlife and from livestock farming. And then all those come together to try to relate exposure from contaminants to diseases and health impacts. There are also the social costs of pollution that we try to incorporate into our studies of contaminants and contaminant chemistry. There's a pretty substantial time lag between the release of pollutants and that when we become aware of the consequences of those pollutants in the environment and ultimately come up with some kind of action. So what is water quality? Well, in a nutshell, it's really a physical, chemical, or biological composition that affects its intended use. And water quality or water pollution has meanings to different users and uses of water. And very often it's not possible to predict intended use. We most often compare water quality to drinking water, such as the chemicals and microorganisms that we measure that can affect human health. And we try to compare those measurements to what we think are potential for exposure, toxicity, and our methods for detecting those chemicals or microorganisms. Water quality monitoring is really designed then to ensure that that chemical or microbiological composition is adequate to meet intended use. Those uses can range from drinking to irrigation, both for row crops or food crops, as well as habitat for fish, recreation for human uses. And who does this? Well, there are a lot of people, a lot of organizations that are involved in monitoring. It really doesn't fall to any one group to do water quality monitoring. One question that I've been very interested in the past several years and probably going into decades now is, will there continue to be enough water of suitable quality for agricultural production into the future? Agricultural production is really dependent on water of sufficient quality, and I don't think that we spend enough time really to predict whether or not we'll be able to maintain water quality for agricultural production. There's little regulation of irrigation water quality, for example. We have increasing freshwater demand at various locations across the globe. And coupled with that, we have a changing climate. We have areas of very scarce freshwater resources. We have areas where we're reusing water and we're not really monitoring the quality of that water after it's been used for one purpose. And ultimately, we have increasing global chemical use, pesticides, pharmaceuticals, and other chemicals, and these are all contributing to changing water quality in agriculture. In the US and other countries, we have very little regulation of agricultural wastewater. It's really not monitored very closely. In our country, there are very few treatment methods that are used for, say, for example, livestock wastewater. And we typically use it simply directly from the source as a nutrient source for crops. So what are these wastewater microcontaminants, or the emerging contaminants that everyone talks about? Well, our wastewater is typically characterized by solids content, oxygen demand, and nutrient content, as well as some bacteria and metals. Emerging contaminants or microcontaminants are new, and I put new in quotes. They're really low concentration contaminants such as pharmaceuticals or drugs, antibiotics, steroid hormones, personal care products, plasticizers, surfactants, flame retardants, and even metabolites of all the above. These are new chemicals of concern that we now know something about because we can measure them in fairly complex matrices. And really the ultimate purpose of this is to understand where they occur and what we can do to control the risks to water quality. But we have multiple inputs of these emerging microcontaminants, both from animals and from human use. In agricultural environments, we tend to be dominated by farm effluents and manure application. In human use of these contaminants, most of this goes into our sewage treatment systems. Both of these sources wind up in our rivers, streams, and lakes, and even occasionally end up in groundwater. As I mentioned, really the point of measuring these compounds is to understand the fate of these chemicals and the ecological or human health effect of these chemicals. As we release these into the environment, things like pharmaceutical residues can occur in manure that's used as a soil amendment, municipal biosolids, or even wastewater that's applied to soil. And this soil that's receiving these compounds is a reservoir and home to a variety of bacteria and other microorganisms. In agricultural systems, very often we see loading of emerging contaminants from livestock use, both from the storage of the manure and slurry, and then ultimately into soils where they are used as a soil amendment, and finally as runoff into our streams and waterways. So there's a variety of different emerging contaminants ranging from steroid hormones, antibiotics and antimicrobials, stimulants and pesticides. Each of those groups has different potential effects after they're released in the environments that ultimately can lead to a consequence. For example, steroid hormones can lead to endocrine disruption of fish, either feminization or masculinization that can change the population composition, say, of a fish that's affected by those hormones. Antibiotics can lead to antibiotic resistance in the environment, as well as potential for proliferation of antibiotic resistance and pathogens. Pesticides, new and legacy types of pesticides and antibiotics can all affect microbial respiration, ultimately changing the way nitrogen is cycled or in the environment, and also affect primary productivity. So really the guiding rule is to measure these as accurately as we possibly can, and then understand what the effects are when we make these measurements. And here's just a few examples of research that we've undertaken to study the occurrence and effects of different emerging contaminants. It's really a challenge to connect use with effect. I've been very interested in antibiotic use, especially in livestock production. Antibiotics are used in human and animal medicine, and in livestock production, they've been used as growth promoters. Our increasing use of antibiotics in livestock production and animals has led to the increased incidence of antimicrobial resistance. These mostly come about because of the heavy use of some antibiotics, such as tetracyclines, for growth promoters. Antibiotics in agroecosystems is a very interesting topic, especially from a One Health standpoint. We're very interested in how these compounds are released into the environment from animal use, and also from human uses, and then how they can affect human health from their release into the environments, whether through the development of antibiotic resistance, our food quality, as well as changing our ecosystem functions. One of the things that's I've been involved with over the past 10 years or so is looking at the occurrence of specific groups of antibiotics. This is a paper where we tried to rank different types of antibiotics based on predicted concentrations in soils and their use in Europe, as well as their persistence in the environment. Well, it's very difficult to measure these compounds accurately. They occur at relatively low concentrations in complex environments, complex samples. I'm just going to run through a couple of examples of how we do that. Well, we use a process called liquid chromatography to separate these on the instrument. These are water-soluble compounds, and that's one reason we use a liquid chromatography system as a way to separate these. Our conventional liquid chromatography detectors are typically not sensitive enough to detect these at the concentrations that we might measure them. So that it turns out our mass spectrometer is really the most sensitive and specific detector available. There are a lot of options, even for a type of mass spectrometer that we would use. We've had experience using an ion trap as well as a triple quadrupole at the Water Science Laboratory. And really the ultimate question is, what is this little bump and how much is there, is the question that we're answering when we're measuring these in the environment. Well, one of the advantages that we've learned over the past several years of using mass spectrometry is in the advantage of a tandem mass spectrometer. This top figure shows a total ion chromatograph of an antibiotic. And then we compare that to a selected ion monitoring where we're really only looking at that particular chemical that we want to measure. I believe this is danofloxacin. And then we look at this in the same instrument in a tandem quadrupole mode. MS-MS is what we call it for short. And we can see we have a much better signal than we would if we looked at the instrument just using a single quadrupole. So really the point of using MS-MS is to give us better sensitivity and more confidence in detection. One of the things that we run into quite frequently in environmental samples is matrix effects. Even when we're using a tandem mass spectrometer, we can have suppression or enhancement of the signals that affect our ability to detect and quantify these chemicals. And that's what this lower diagram shows, is the change in signal just from analyzing a real sample versus a standard, is that we get a lot of variability during the chromatograph and the detection process, mainly because of all the other chemicals that occur in these samples. Liquid chromatography tends to not be as selective as, say, gas chromatography does. So we have quite a few issues in making sure that we're able to separate the compound that we want to detect from everything else that has a similar mass. This shows the chromatograms for chlorotetracycline and isochlorotetracycline, which is a different form of chlorotetracycline. They may have similar masses, but they have different retention times. What form of chlorotetracycline occurs in the sample is really important if we're looking at the antibiotic resistance of chlorotetracycline. Is it really due to this active ingredient, or is it due to this other form of chlorotetracycline? Another issue that we run into when measuring antibiotics is the formation of adducts. Adduct ions tend to be formed in the mass spectrometer source. And for some chemicals like monensin, which is what you're seeing here, the formation of a sodium adduct is very common, and it can interfere or help with detection depending on the conditions of the separation. And finally, we've learned that we want to be able to detect both the parent compound and its degradation product. Here's a chromatogram for erythromycin, which is a common macrolide antibiotic, and its degradation product called anhydrate of erythromycin. So really we want to sum these two compounds together to get the total concentration of erythromycin originally present in the sample. Well, one of the projects that we've used our antibiotics analysis for is relating the occurrence to the type of livestock production system. This is a study that I was involved with several years ago, looking at steroid hormones and antibiotics in groundwater impacted by livestock waste. And we found that monensin, which is commonly used in cattle production, only occurred at facilities where we had cattle production, whereas a ractopamine would only occur in facilities where we had swine production. And both of those are specific to certain types of livestock facilities. One of the methods that we've used over the past several years to measure antibiotics in runoff or surface water systems is known as passive sampling. These are polar organic chemical integrative samplers, which allows us to concentrate these chemicals over time at a specific location. These are small quantities of a polymer sorbent that are contained inside a filter membrane. And then this stainless steel canister is dropped into the water and allowed to concentrate that chemical over time. We can retrieve that sorbent and analyze it in the laboratory and relate that to a time-weighted average concentration at that location. And what we find is that we can relate the incidence of specific types of livestock production in a watershed to the occurrence of specific types of antibiotics. In this watershed, for example, we saw a pretty high incidence of monensin. Again, that monensin is a pretty common ionophore used in cattle production, very high concentrations of monensin. We also found lincomycin, which is typically used in swine operations for treating dysentery, also occurred at pretty high concentrations. In that same study, we're able to relate the occurrence and concentrations of these chemicals to flood events in the waterway. The upper graph or the bar chart shows the concentrations of antibiotics such as lincomycin and monensin to flood events in the watershed at different times of the year. So another project that I've been involved with is looking at the unintended consequences from antibiotic release in watersheds, both through runoff and application to soils. Along with increased pressure for antibiotic resistance, we can now say that there's probably changes in soil microbial community composition and effects to nutrient respiration. This particular study looked at the effect of pulses of antibiotics to soils. We could see that there was basically a stop in the production of nitrate when antibiotics were added to the soil. We were inhibiting nitrification, and this effect likely happens in the real world and translates into the loss of nutrient transformation capacity in the ecosystem. So what can we do if we're releasing antibiotics into the environment through a manure application, for example? We found from this study that we can introduce buffer strips or grassed hedges. This would reduce the mass loading of antibiotics and antibiotic resistance genes in manure-treated soil. So even just simple conservation measures like a grassed buffer can reduce loading to the environment of antibiotics and other emerging contaminants. So in summary, I'd say the future of freshwater conservation, we definitely have increased food demand from increased population. It's placing an ever greater stress on our freshwater, especially in agriculturally intensive environments like Nebraska. These increasing stresses are likely to impact water quality in ways we may not expect. We definitely need to prioritize, monitor, and evaluate the effects of these contaminants to conserve and better manage our freshwater resources. And I'm certain from this research that measuring water quality will require interdisciplinary research and efforts by analytical chemists, engineers, biologists, and other scientists to assess the impact and sustain future food production, especially for 9 billion people. And then this is my last slide, just to acknowledge this work couldn't have been possible without the Water Sciences Laboratory. We just celebrated our 30-year anniversary. We received funding from the Nebraska Research Initiative. And then those projects that I mentioned in my presentation were supported by a wide variety of grants from these funding agencies.
Great.
And I think I'm on time.
Yeah, thank you, Professor Snow. Yeah, and you add some information that we just started our first webinar with Dr. Laura Kahn and Dr. Christina. And Dr. Laura brought us an information that by 2030, we will have a total fecal mass as estimated to be 4.6 trillion kilograms per year. So imagining that we have all this contamination, we have a huge problem to manage and to prevent. So thank you very much for sharing your experience and your high-tech work in Nebraska. We thank you very much. And now we're gonna introduce our next panelist, Dr. Julio Cesar Palhares. And Dr. Palhares is a senior scientist at Embrapa, the Brazilian Agriculture Research Corporation, at the National Research Center for Livestock in southeast of Brazil. Dr. Palhares is graduated in animal husbandry and holds a master's degree in agronomic science. He holds a PhD in environmental engineering science with focus on water resources, integrated planning from University of São Paulo. His research has focused on dairy and beef cattle waste management, working on the environmental impact of animal waste on water resource. He works also with water management of farms and watersheds and water footprint. And he works also at academic advisory of graduate and postgraduate students projects. So welcome, Dr. Palhares.
Thank you, Luciana, for the introduction. And I also should thank for Professor Paulo, Professor Marcelo for the invitation. Okay. I'd like to talk with you about water and agriculture. And when I talk about agriculture, my main thoughts will be about livestock, okay? Because I'm an animal scientist and I work with farmers and animal industry about how to manage the water in these activities, okay? So my focus will be in livestock, right? And I'd like to bring a more macro vision than Daniel, okay, about water in Brazil and some comparisons with the United States and the challenge that you have to manage this research in a better way, okay? So first, why water, okay? Why should you care about water in quantity and quality? Because it cannot be produced, okay? No substitutes to water. It's abundant in some places and scarce in others. Brazil and the United States are rich countries in water research, but you have a lot of problems about water availability around the world, all right? Mainly when you talk about produce food, okay, we need a lot of water in quantity and quality. And maybe in countries like Brazil, we have regions with a lot of water to be used and consumed. And but you have a lot of regions that have conflicts about water use. Mainly in the center part of Brazil, when I am in São Paulo state, that is it's a most industrialized region in Brazil, all right? So you have a lot of conflicts to use this water. Water is an essential element that everyone needs, but not everyone can afford. It has multiple productive and consumptive uses, okay? It's a subject to monopoly control, both public and private. It has low unit value and is difficult and expensive to transport and distribute. It cannot be easily measured. And when you talk about farms, okay, measure the water consumption in a farms, we have a lot of knowledge to do it, but sometimes this technology is too expensive to the farmer, and it is a big challenge. And you can't manage what you aren't measured, all right? So measure the quantity of water that you are using to produce foods is a main topic. Has different qualitative standards depending on users, as Daniel said to us, okay, depending on the use that you do of water, like irrigation, drink water to animals or water to humans, okay. There is a kind of standard, a quality standard. So you can know these standards and manage and treat the water to reach these standards. It is polluted, but not easily treated. Okay, so you have a lot of technologies to treat the animal effluents or the water to serve to a human or to humans, but sometimes mainly in Brazil, this treatment is too expensive. Okay, so the man smart thing, okay, the smart thing is not pollute the water, because if you pollute it, you have to treat, and the treat means spend money. All right, it's often subject of regulation and price control, and it's a very sensitive and controversial topic which everyone is interested. All right. So I will present to you 3 scenarios, all right? And these scenarios are happening in the same time, okay? The first scenario is the blue sky, all right? When you have a lot of water to consume and you have water in quantity and quality to produce food. You have a gray sky, okay? When you detect some problems, choose this water. And you can have a black sky, okay, where water is a big challenge to use and to produce food. Let's start with the blue sky. In this graphic, you can see that one question that always ask me is, will the water in the world end? No, okay. You listen about the water cycle, okay, you see it in these slides, all right, but the water isn't end in the world. But you can see in this graph that after the Second World War, and when you start a big process of industrialization in the world, and you can say that we start the process of green revolution when you start to produce a lot of grains or animals per hectare, okay, a huge intensification of the agricultural systems. The use of water increases a lot in the world, okay, and it is a tendency, all right, and here we have we are seeing a vision of the world, but when we talk about water, the world is important, but the region, the catchment, the basin, it's most important, because we live in the blue planet, okay, but in the blue planet we have a lot of regions with problem of scarcity, all right. In this graphic, you can see that in Latin America and North America, okay, with exception of Oceania, all right, but Latin America and North America are regions with a lot of water, okay. So in Latin America, we produce a lot of food, in South and Central America, and North America, Canada, Mexico, and the US also produce a lot of food. One of the reasons to it is because we have a lot of water in quantity and quality, okay? You can see in Europe or in Asia, okay, the water availability is too limited, all right? So countries like China, India import a lot of food, and we can say that import a lot of water in the form of food, right? It's a blue sky too. Is this cost of water significant in the cost of agricultural production? I think that no, okay. when I studied the US reality and in Brazil, the impact of the water in the cost of production, it isn't significant, all right? And unfortunately, you know that one thing that don't have value, the human don't have value to this thing, okay? And nowadays, the most important mechanism that you have to give value to a thing is put a value, put economic value to this thing, okay? It's a big discussion because our people and farms of animals and vegetables that live in this planet need water to live, okay? And when you put economic value in the water, you can limit the access of water to some people, all right? And it's a social problem. So it's a discussion. But when you talk about agriculture, it's an important discussion, okay? You should put value to water, all right? Should best manage this research. And let's pass to the gray sky, okay? One important question that society always asks us is, agriculture is the largest water consumer in the world? Yes, all right. You can see in this graphic that between this period, more than 100 years, all right, you see that agriculture is the main consumer of the water in the world, okay? And it's the average of the world, and but it depends on the level of industrialization of each country. I will show it to you, okay? In the graphic, you can see that in high-income countries, okay, industries, we can compare the consumption of industry with the consumption of agriculture. But in upper and middle income countries like Brazil, all right, the agriculture is the main consumer of water. In the low income countries, like most countries in Africa and Asia, the majority of the water consumption is to produce food in the agriculture, all right? So this vision brings us a question, okay? Are you doing it with efficiency, okay, with productivity? It's a big question to solve, all right? But mainly in industrialized countries like US, the consumption of water by agriculture is very significant, all right? It is a vision of Brazil, okay? It's a data from the Brazilian Water Agency, okay? Every year, the agency publish a book about the waters in Brazil, and you can see the majority of the consumption, 78% of the water consumed in Brazil was consumed to produce food. 67% in irrigation and 11% in animal drinking. Here we have just considering animal drinking, okay? We are not talking about the water footprint here, all right? And the irrigation is just the practice of irrigate the crops, all right? But it's the common situation in Brazil, and we are a country that produces a lot of agricultural commodities, and when you produce commodities, you need a lot of water in quantity and quality. So this kind of situation make the society ask to us, why are you consuming this water, okay? And you should show to the society that we are doing it with efficiency. To have an idea, on average, for every Brazilian, there are almost 42,000 meters cubic of renewable fresh water annually. Brazil has almost 12% of fresh water in the world, okay? If you think about it, just one country in the world take 12% of fresh water, okay? It is we are a rich country in water, but the availability of this water, it isn't homogeneous around the country. As you see in this map, okay, the most of water availability is in the Amazon basin, in the north part of the country. In this graphic, it's from Brazilian Water Agency too, okay. You can see that beef and dairy represent 88% of the water consumed in Brazil, okay. In the second, we have the swine, after poultry, okay, horses and buffaloes, and goat and sheep, all right? And in this map, you can see that depending on where you have this production, these animals, okay, we have the consumption of the water. So in the north part, as I said, you have a lot of water in availability. But in the south part of Brazil, where are the more or less 60% of our swine and poultry production, we don't have a lot of water. Okay, here we have a big conflict about water because in the south and the center-east part, we have a lot of industries, we have the big cities, and we produce a lot of crops and livestock, okay? So the conflict is a common place here in this region. The conflict about water in quantity and the conflict about water in quality, because here we have a huge animal concentration intensification process in the farms. And as Daniel showed to us, when we have this kind of process, the effluent, the organic load of the effluent is a big problem, okay? When we talk about nitrogen, phosphorus, potassium, antibiotics, and the other things, right? One important question is, do you measure the water consumption of your product system? In my opinion, no. And I can talk about Brazil. It isn't a commonplace, okay? When you find a farm that have a water meter like this, okay, and are measuring the water consumption, unfortunately, it is an exception, all right? And when you talk about water consumption, we're talking about the animal drinking water, the consumption that you use to service water, like wash a milk parlor, all right? And now and in the future, you have to understand the consumption of water by the feed that you use to feed the animals, like corn, soybean, and irrigation. We can transform these products in water and calculate the water productivity of the meat, the water footprint of the milk, okay? So our idea of consumption have to change, okay? In the past, we understand that the water consumption in livestock is just animal drink water. No, okay, it's a past idea, and if with this idea you can't progress in our water measurement. Okay, you have to change this kind of idea. It's a good example. It's an American farmer. Okay, it was published in a technical magazine last year, and you see the title, Farming for a Better Future. In this farm stood, that is the farmer, okay, has a water meter to measure the consumption. He uses this number to monitor animal health. The water consumption typically goes down a day before pigs become sick, indicating a problem, okay? Water consumption is a big indicator to evaluate the animal development, okay? We can relate water consumption with the health of the animal, the welfare of the animal, okay? We can use the water consumption to detect if you have some problems in the water distribution system, okay? And it is the farmer of the future, but it has to be the farmer of the present, okay? Studies also have a bioreactor to monitor the nitrate levels in the runoff of the effluent, okay? Because this farmer used the effluent as a input in the agricultural areas to live in nutrients and water to the crops, okay? But you have the risk to have a runoff in this kind of threats, okay? So institutes are monitoring this kind of rats, all right? It's a very important situation, and it must be example to all farmers in US and in Brazil, okay? But unfortunately, nowadays it is an exception, all right? And the black sky, the global warming is a process that we are suffering, okay? You know that the pandemic could be a small thing if you compare the worst scenarios when you talk about global warming, okay? And if you compare the carbon emissions in the last years in terms of absolute emissions, okay, it is increasing, okay? It's a problem because you are talking a lot about global warming, but until now you can't stop the emissions, okay, in absolute term, all right? So you have to take care with it because it's too serious, all right? So for example, in US, in this study, there are a record of 22 weather and climate disasters across the West last year, with a price tag exceeding $1 billion, according to the NOAA. Since the 2060 billion-dollar disaster in the US have cost more than 600 billion, a record for a 5-year span, okay? This photo is from BBC. I think that this photo has more or less 5 years ago, okay? Pray for rain, all right? It is in California, US region, where you have a lot of problems with water availability and water quality, all right? And maybe it is the last thing that we can do, pray, okay? But you have to change this kind of behavior, all right? Do you have a water measurement in your production system? And are you define water measurement as a daily use of knowledge, practice, and technologies that guarantee the supply of water in quantity and quality? And my answer to this question is no, okay? You don't have water measurement, mainly in Brazilian livestock production. And when I studied some experiences in the US, I can conclude too that in livestock, in US livestock, water measurement is too common too, all right? And why don't you have water measurement? Because water is a common research. The culture of abundance, it's a big problem to us in Brazil, and because in our culture we have a lot of water, and when you put it in the red of the people is a challenge to change this idea, all right? Water is not understood in its 3 dimensions: feed, input, and the natural research. Mainly in a livestock system, water has these 3 dimensions: feed, input, and the natural research. Reduce knowledge of farmers and the professionals about water and agriculture. And the water is considered a free commodity, not being considered in the production cost, as I said. And the water management advantage to us: information and knowledge about the relationship between water and agriculture, performance, and the production system. Water performance indicator, we can produce a lot of indicators to manage the water and our production systems. Implementation of best practice, okay, about water in the farm. Water efficiency of the system and the products. Environment more balanced, economically more profitable, and socially more valued agriculture, okay? The society wants it, all right? And agriculture will not be understood as an explorer of water, but an efficient and effective transformers of water into food. It's our challenge, okay? Show to the society that yes, we produce food and it uses a lot of water in quantity and quality, but you are doing it with efficiency, all right? And what is the water efficiency? Efficiency is liter of water per kilo of products, and the water productivity, kilo of products per liter of water of our food. Okay, we have little knowledge about it. Here some examples. It is a study from the Food and Water Institute. Okay, in the web page of the institute, we have these maps, the Global Wide Gap and Water Productivity Atlas. I took an example of Brazil, the soybean in Brazil. The water productivity is on average 7 kilograms of soya per millimeters of water per hectare. Okay, but in this study you can find a lot of data about US and other countries. It's kind of study is very important because we need this information to better manage the water. All right. Here I stood that I and colleagues from Germany, we published last year, and we evaluate the water productivity of swine and poultry meat, okay, in a salt basin in Brazil, and we stipulate 4 scenarios to evaluate the impact of the scenarios in water productivity. And in summary, when I do the best in agriculture, okay, when I have a high productivity of soya and crop and maize, that are the major feed in the swine and poultry production, okay, the water productivity increase. Okay, if I compare this point with these points, okay, here I have a low crop productivity. So there isn't water productivity of livestock products if you don't have a best practice in agriculture. Okay, the relationship between agriculture and water productivity in livestock is totally direct. All right. And here is water study that we published last month in January, when here we calculate the water footprint. It's a methodology that I think that you know very well, like carbon footprint or ecological footprint. Okay, here we talk about beef cattle. Okay, and that in the first 2 phases, we produce these animals in pastures, and we finish there in a feedlot. Okay, we have 2 kinds of diets with core products and with soy and soybean, and we calculate the average water footprint and the individual water footprint of each animal. Okay, and when you see the average water footprint and compare with the minimum and maximum water footprint, you are talking about the same animals. All right, you can see the significance of the difference between the minimum and maximum footprint. All right, so it's bringing to us an idea about if you want to manage the water with precision, maybe consider the average can be a mistake. Okay, nowadays you have knowledge and you have studies that can afford us to calculate the water, the carbon, or the land footprint to each animal. It's important, okay, to manage the research with more precision. All right. People, markets, new values, new ethics. Okay, the society is always changing. Okay, and are present to us that work with food, new values, and new ethics. All right. Here, example from UK. Okay, it's a group of 6 civil organizations that put a goal that in 2030, okay, they want to reduce the consumption of meat and dairy in 50%, and they establish 8 goals. Okay, you can see antibiotic use, water scarcity. Here, example about water, how they intend to do it. Okay, in a basic, better, and the best scenario. All right. Here about the use of antibiotic. Okay, they intend to, as you can see here, to transform the conventional system to organic system. Okay, you know that in organic farms You can't use the antibiotics as you use in a conventional farm, okay? So it's a target to this group. But things like this movement, like it's okay, will be very common in the world, okay, in a lot of countries, all right? And here I bring this example as a black sky, but it depends on of the side that you have, okay? If you nowadays, if you are the side of the agribusiness, okay, the majority of the agrobusiness actor understand it's like a treatment, all right? But you are in the side of environmentalists, you understand it as an option, a good option, okay? The new proteins, the vegetable and cell-based proteins, okay? That's one of the advantages, but I put it as a question, okay? More environment friendly. There are some studies that show to us that to produce a beef or a milk in a vegetable or cell-based way, you consume less water, you emit less carbon, all right? Maybe you can use more energy, but it's a very initial process, okay? And you have to demonstrate that these new proteins have advantages in environment challenges, all right? The water cycle, all right? Understanding the water cycle is essential to promote the correct water measurement and the proposed best practice. And unfortunately, when I teach the water cycle to my students in university, they have a poor idea about it, okay? What is the water cycle? I like to say that you have the four fantastics, all right? The water, carbon, nitrogen, phosphorus cycles, all right? And when you produce food, you are talking about manage these four cycles to produce these foods. So you have to know very well the cycles and how you can impact the cycles, all right? Understand the water cycle also means rethinking our concept about water consumption. As I said, considering the feed that you use to feed the animals as a consumption, all right? I'm finalizing. What I understand to be water prepared, recognize water's affinity natural research, understand that water is a local source available in a river basin, have knowledge and technical capacity to manage the water, decide considering all productive and economic aspects as well as water and other environment aspects, all right? And I have to put to discuss because it's an important point. Many people in the world are hungry, all right? According to FAO, we produce enough food to feed everyone. Hunger is not just a matter of quantity. You just need to produce more food, but you should give access to food, all right? Hunger is a political and a social issue. Producing more food without solving social issues can mean wasting natural resources. When you talk about foods like maize, soy, meat, okay, we are talking about commodities. There are a lot of people that earn money with it, and these people never produce a seed or a liter of milk, okay? It's a discussion, okay? We can do it in a simplistic way. All right, there is a social and political problem to solve. The color, the sky you have depends on our choice. To finalize, we can talk about water and agriculture, we can talk about water and the agribusiness, and we can talk about hydro-agrobusiness, okay? There is no food production without water. Every time the production of food will be treated by the lack of water in content and quality. Okay, guys, thank you for attention. Okay, I'm available to the questions. I am in the social medias, okay, and I have a channel in YouTube, unfortunately just in Portuguese, okay, when I put videos about animal agriculture and environment conservation, but in Twitter and the LinkedIn, I'm always putting information in English to share knowledge and to discuss about it. Thank you very much.
Thank you, Dr. Palhare. And you brought some very good and challenged questions to our audience. And you gave a spoiler. Your Black Sky Day is going to be our discussion also in the next webinar on Wednesday. We're going to talk about climate change and global warming. So this is a spoiler, and you did it as well. So thank you very much. And I will invite Dr. Marcelo Molento. He will conduct our discussion session. And I will introduce you. Professor Molento is a veterinary doctor, graduated in Brazil. He holds a PhD from the Institute of Parasitology from McGill University, and is currently an associate professor at the Federal University of Paraná, where he coordinates the Laboratory of Veterinary Clinical Parasitology. He's a consultant for research institutions in Brazil, Latin America, United States, Belgium, and the Netherlands. And Professor Molento is also a consultant for parasitic disease and the human-animal interface to the Food and Agriculture Organization of United Nations and to the World Health Organization. His scientific goal is to develop techniques using an integrated parasite control system, the SICOPA, to improve life quality and welfare of animals, humans, and the environment. And he is also the coordinator of a graduate course named Global Health that we have here at Federal University of Paraná. So welcome, Professor Molento.
Thank you very much, Luciana, and good evening or good afternoon, everybody. Thank you, Paulo Pires, also Paulo de Tarso, for the invitation, for having me here. And congratulations to Daniel Snow, to Dr. Daniel Snow, and to Dr. Julio Palhare for their very interesting and insightful talks. I will open the Q&A period by inviting Dr. Christina Peyton-Brewer for her question, because, you know, first of all, she knows a lot of the subject, and also because she has quite a few questions. So please, Dr. Christina, if you want to open your mic and your camera, feel free.
Hello, everybody. It's sunny here in Seattle, which is surprisingly, but it's a thank you very much, Dr. Daniel Snow and Dr. Palhare. Excellent, very important discussion with especially not only the agriculture and all the animals and agribusiness, but everything is coming to the water. And it's especially for us here in Seattle, everything comes to our islands and to the ocean. So whatever's happening on the fresh water, it is affecting the ocean as well. My question is a little controversial, but since we're here as a panelist, I would like to see, and we're talking about agriculture and agribusiness. I have two questions. One of them, I will first go to Brazil, what is the mining and the rupture of the dam that we had in Brazil recently, Brumadinho and Mariana, which also it is the pollutants. So all the toxins and the heavy metals that are still in the water. This water is going to the agriculture, not only for human consumption, but the animals. The animals are there, cattle are there. It doesn't matter if it's a small agriculture production or the big production. So my first question is, how can we measure scientifically, or how can we all get together as different professionals to show that there is, through the One Health approach, there is a risk of human and animal contaminants in the water? So the first one is, what are we doing with the mines? And the second one is fracking. So those two are humans, and we do need to use them because it's our business. And how can we, as diverse professionals, work together to show what is going on with the fracking and mining. Thank you.
I can start.
Yes, please.
Okay, Christina, thank you for your question. All right. It is my specialization, mining or fracking. Okay. In Brazil, we don't have fracking. Okay. But about mining, I think that's a problem in Brazil, in US, in the world. Okay. When you talk about what happened in Brumadinho and Mariana, we are talking about one company, okay, that has a stronger power. All right. And in this kind of situation, the law, the environment law, doesn't function to this kind of companies. Okay, it's very common in Brazil, it's very common in the world. All right, and unfortunately, nowadays we have companies that are stronger than a government, a federal government. Okay, they put a lot of money in the politicians. Okay, to win the election. For example, when we talk about livestock industry in Brazil, we are talking about 4 industry that have a strong power too. All right, and sometimes don't consider the environment law. All right, it's a true. Us as society have to regulate it. We have to show to these companies and to the government that we don't accept it. All right. I don't have idea how to do it. Okay. We know that there are springs around the world that achieve to win this battle against these companies. All right. And I think that you have to learn with these experience and work as a society. Okay, because as an individual, you can't do anything because the other side is have a big power. All right. And about the second question, and I will bring the concept of One Health. Okay, that you have to think about people, planet, and animal. I'm a teacher too. Okay, and unfortunately. I don't know if you agree with me, okay, but you have a problem with our professionals, okay, because when I talk about the concept of One Health or concepts like circular economy or holistic vision of the world, okay, you will need to rethink our professionals, okay, and when we talk about academia or research institution, or the majority of time we are talking about the box. Okay, everyone has your box, think in your box, okay? And when you put a systemic concept like it, you have to open your box, okay? And you have to be open to know the box of the other, okay? And when you talk about environment problems, you talk about the social science. You have a lot of knowledge to solve the environment problems, okay? But the big challenge is social. All right, you have to work with psychologists, philosophers to understand this part of our body. Okay, it's very difficult to understand this part of our body to solve the problems. Okay, maybe it's a philosophy. Okay, but philosophy is important to understand the world and solve the problems.
Mm-hmm. Good. Dr. Daniel, a few words about the questions from Christina. Dr. Christina, please.
Yes, I'm not an economist, but I think the economists call this externalized costs. These are costs that are borne by society or our organization that are passed on through producing goods and services. And I think if we would do a better job accounting for externalized costs, say from livestock production, that we might come up with a more sustainable model for agriculture. Very often we ignore externalized costs to the environment. And if we would just do a better accounting job, I'd like to think that we'd have cleaner water
it is so essential to do it. Huh? So that would be the basic.
Yeah.
Fortunately, we don't. We have another question from Ethiopia, I think, Mezembet Sebat. And the question is related to developing infrastructure, okay? Which would be very important for lots of countries, especially in his case, East Africa, like Ethiopia. Could you guys explore some of your experience regarding infrastructure and water? Not only water safety and water quality, but the right of water.
I don't know as I can answer this question. Okay, sometimes the infrastructure means impact in water. Okay, in quantity and quality. All right. If you don't consider in the engineering of this infrastructure conserve and preserve the water sources, you have problems. Okay, we have to know with the history. Okay, and it's very common in our history as humanity. All right, and in Brazil we also have regions with gaps of infrastructure. All right, and we have to take care with it. Okay, because infrastructure is important to society because it can bring the progress, the health, the education. Okay, but as Daniel said, it also brings externalities, and you can't treat the environment as an externality of the infrastructure. All right.
Mm-hmm. Good. Daniel, any words?
Yeah, I think infrastructure is a critical aspect of managing water. Even in the United States, where we have a pretty well-developed infrastructure for water resources management, it's not very well maintained. You know, it's far easier to install and develop an infrastructure than it is to maintain it. In developing countries like in Africa, I'm sure that they're struggling just to provide safe drinking water to, especially to rural Africa, and that's one of our biggest health challenges now, is just making sure that everyone has access to safe drinking water across the world. So I think that should be our priority for any country, is to make sure that everyone has access to safe drinking water.
Good, thank you. Paulo, you want to make some comments?
Question. Daniel, we know that you have a very different governance of the water in Nebraska, considering the natural resources districts. Do you think that nowadays you have a control of the quality considering the health of the population, or for your, in this case, doesn't matter for the government about the quality considering the health problem?
Yes, so you're talking about our natural resources districts?
Yes, and if they are considering nowadays the health problem, or just the quality for agriculture or things like that.
I suppose what is true in Nebraska would be true for any government, is that each district has its own board of directors, and the perception of how well they're managing their water resources really varies depending on that board. They have to operate within our state and federal guidelines, but there are there's a lot of flexibility within those state and federal regulations. I do think we have some very progressive natural resources districts that are extremely concerned about water quality. And those districts in particular are doing a very good job at monitoring and trying to manage water quality issues.
Yeah, this was something that you mentioned in your talk regarding the little regulation that water has in the world, and for sure, U.S. and some countries in Europe, the regulation is much more advanced. But although advanced doesn't mean fair. It means yeah, there's lots of gaps here and there, right?
Yeah, we seem to be better for cities. We're doing a little bit better job at managing, say, drinking water quality for cities than we are in rural areas, both surface and groundwater. And I suspect that's just because there are more people that are affected in a city than there would be in a rural area.
Yeah, fantastic. Yeah. Dr. Julio, Paulo, you have another question?
No, I'm just asking because I know that you have this problem with pesticides, nitrates, contamination, and I'm curious about that. Are there any natural resource district working with this and antibiotics in the water and things like that?
So Nebraska is a groundwater state. We have this huge High Plains aquifer system that underlies over 2/3 of our state. So because of that, our groundwater quality tends to be heavily impacted by agriculture, contamination from nitrate and pesticides in particular. There are NRDs that are quite progressive in trying to reduce loading of, say, fertilizer contamination to the shallow groundwater. The problem is, and it gets back to one of my slides, is that we usually react to problems far too late. We become aware over time and then we react. And because there's such a long time lag between awareness and finally doing something about it, it will take many decades of effort to try to undo the levels of pollution that we are currently facing.
Okay, thank you.
Great. Yeah, thank you. Dr. Julio, you mentioned something regarding the water management and how could farmers in Brazil improve the way they manage water, because for sure we waste too much water and too much good water in that sense.
Yes.
How do you have any practical example that you are following or your work in some areas, maybe São Paulo or Mato Grosso?
I think that the most important example that I can do nowadays, we are working with in partnership with a big industry, okay, one of the biggest in the world when you talk about food, all right, and this industry, okay, 2 years ago asked us to help them to improve the water management in our farms, okay? Because the farmers produce the milk to the industry, okay? And they want to start the water management in the farms. And the first step that we put is install the water meter in farm. So nowadays we have more or less 200 farms with water meters in a pilot study, okay? When you measure it monthly, okay, the concept of water. And in the first time in Brazil, okay, this industry create a program that they give to the farmer a premium of 7 cents of reais per liter of milk, okay? If the farmer put the water meter, if the farmer builds the structure to reserve the manure, okay, and after it put in the field, okay, this farmer gives 7 cents of reais per liter of milk. It's very important, okay? It's the first time that's happened in Brazil, okay? And a lot of farmers start to enter in this program because of it, okay? As I said in my presentation, the money is an important mechanism that you have to move the people, all right? So it's a good example, but I have a lot of examples that individual farmers ask me and ask help to put the water meter, to understand how to measure it, but it's an exception, right? It's exception. Our main task is this exception be the common sense, okay? As I said, it's impossible manage the water if you don't have how much water we consume, all right? So it's the first step. After it, you measure, you know the water behavior in the farm, you propose best practice, okay? Because there is a variation, there are farmers that consume a lot, and there are farmers that have a big efficiency, water efficiency. You have to learn with these farms, okay? And at the end, what we want, the water measurement and improve the water efficiency of the product. Because the society is asked to us, how much water do you use to produce 1 kilogram of meat, of dairy, okay, of milk? It is important. We have to answer this question.
Great, fantastic. Yeah, I guess that's a future challenge as well, because if we let things the way they are, we are sure going to run out of fresh water or sparkling, just good water, let's say. Luciana Pires is asking a question regarding the future for water after COVID-19. And she mentioned something like more antibiotics, more ivermectin in the soil, because we are using, especially in Brazil, we consumed during 2020, we consumed 43 million packages of ivermectin. That's insane, totally insane. Yeah. So I know that Dr. Daniel Snow uses MSMS, and so you have work forever to measure all the contaminants in the water. If you want to speculate something regarding that.
I've talked to colleagues about the increased use of pharmaceuticals, such as ivermectin, because of COVID-19. And I suspect we are releasing much larger quantities of specific drugs into the environment. And as we're finding out through other studies, this release is going to have unintended consequences, not just for the environment, but probably for human health. So if we could do a better job predicting what the consequences for using more of these drugs will be, I think we'll be smarter consumers, I guess, of pharmaceuticals.
Yeah, because ivermectin, I worked with ivermectin for the last 25 years. So ivermectin doesn't metabolize, to an inactive form, let's say. It stays in the soil, it stays in the water for more than 3 or 4 months, let's say.
Yeah.
And it's very aggressive when it's outside.
Yes, and I recall from some other projects that I was involved with, it has some pretty significant ecological effects, ivermectin in the soil. So, we don't really account for those effects when we administer either to ourselves or to our animals.
15 years ago, I made a calculation just for one commercial compound, which is the leader on the market. It was something regarding 15 tons of ivermectin per year for one brand in Brazil. So
Yeah.
this is a lot. But if you multiply by 43 million packages, now in the sewage of the city,
Yeah.
we are not prepared for cleaning the sewage, in most of the cities. This will be a major impact. This can be a major impact for sure, because ivermectin is also an antibiotic. Okay, it's as a second hand will be like selecting many different bugs and worms and viruses and bacteria, blah 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 blah. So we're walking in a thin ice for sure. Yeah,
I agree.
So, yeah, Dr. Julio, you have
No,
any?
don't. It isn't my specialization. I don't have.
Good. How are we doing for timing?
Yes, I think that's my time to
Yep.
say thank you to Professor Marcelo Molento. Thank you, Dr. Julio Palhare, and nice to see you. And thank you very much, Daniel Snow, for your participation in this.
Pleasure.
And thank you, Luciana, Amber, and Francis for your brilliant work today. A good night for everybody all around the world. Thank you, guys. Bye.